Please raise your hand if you've ever played with Lego bricks before. All right, that's about 98%. Please raise your hand if you've never played with Lego bricks before. Okay, 1%. So for those of you that don't know what Lego bricks are, they are small plastic construction pieces that you can connect together to build any structure you want. If you have played with Lego bricks before, you might remember accidentally connecting two pieces together in the wrong way. It's a simple mistake. You may not have been paying attention, or your hand might have slipped, but it's a simple fix, right? You apply a bit of pressure, and your two pieces come apart. And you're free to reconnect them in any way that you'd initially wanted. But now imagine that your Lego bricks are 10,000 times smaller than the width of your hair. And simply applying a bit of pressure won't disconnect them. You'll just have to throw those pieces away. Now, when working at a microchip manufacturing company, you encounter these sorts of problems daily. Take Susie, for example. She works tirelessly, trying to stack layer upon layer upon layer of incredibly thin materials to this nanometer level of precision to build a functioning microchip that we use in our phones, for example. Now, she only really finds out whether her microchip works at the very end of the fabrication process. If the stacking is even slightly off, the functionality of the entire chip is compromised, and her whole day's worth of work might just go to waste. So the research that I do in our group tries to help Susie along the way by offering her tools to verify that what she's stacking is correct. And I do so with light. Now, light is great because, first of all, it's non-invasive, so we don't damage the structures or materials that we're trying to see. And secondly, it's incredibly fast. We can get a lot of structural information, like cracks, holes, crystal orientation, and any other defects in just the blink of an eye. But using light also presents us with a challenge: the diffraction limit. The small features that we want to resolve are about 500 times smaller than what light can see. So traditional bulky optics, like lenses, simply cannot capture these tiny details. This is where Metasurfaces come in. Metasurfaces are truly a revolution in optics. They are ultra-thin patterned surfaces comprised of many different little shapes, like a flat Lego brick. And they are a groundbreaking piece of technology in fields like flat optics, augmented reality, virtual reality, optical computing, and many, many other cool things. And Metasurfaces can beat the diffraction limit. Now, simply by changing the shape and the symmetry of the shapes on these surfaces, we can tailor their optical response and measure very strong signals in response to tiny, tiny nanometer changes in their environment. And because Metasurfaces are ultra-thin, we can actually integrate them on top of microchips and detect tiny defects or misalignments in our structures. So I work together with ARCNL, the research institute around the corner from AMOLF, and ASML, the famous company that develops technology for microchip manufacturing. And together we ask ourselves questions like, what is the best metasurface design or pattern to be able to achieve the highest level of sensitivity? How can we extract the most amount of structural information from a single optical measurement? And can we use light of any wavelength to perform this measurement? Ultimately, we hope that Metasurfaces will redefine metrology, that we'll be able to detect tiny fabrication errors along the way and make everything much faster, cheaper, and more reliable, and the lives of chip manufacturers, like Susie's, much easier. Thank you.